Can everyone hear me on Zoom? Let's see. Yes, perfect. Okay. So I'm trying to use, it's a bit too loud. So I'm trying to use some headphones for those on Zoom to hear me better. So we'll give it a trial this lesson. So let me know if this will be better with the sound. Can everyone hear me in the classroom? Yeah. So. Okay, shall we get started? So, a few quick updates. So we have updated the assignment 3, and we have added an additional problem for linear regression. And so my TA Swati made an announcement, I think yesterday. Yeah. I'm also trying, so these are wireless headphones for people on Zoom to hear better, because sometimes when I get too far away from the laptop, they won't hear me. So we're giving that a try today. People are still coming here. So last time we started talking about decision trees and how we can build these classifiers, and yeah. Oh, this one. Oh, I see. Thank you. I have to swap it. No. So, screen share. It's not good, no. What do you see on Zoom now? Oh, still this. Yeah.
Maybe it's a setting.
Ah. 1 second. This is why it's helpful to have this this TV, because I can see what people on Zoom actually see.
Maybe it's
Wait, where? Use slideshow. Uh-huh. Yeah. So now this is. Can everyone hear me on Zoom also? Is the sound good? I hope so. Let me know, Swati. Yeah. If can actually also hide this. Okay, so last time we started talking about decision trees and how we can make decisions. We can make classifiers by building together many of these decisions. So, for example, we take some action, like if we're hungry, we take some action, otherwise, and so on. And we ask all these queries, and this is how we split the state space with these boundaries. So, and we saw an example of how we can build a decision tree from a data set, from a toy data set. So if you have, for example, if I'm deciding whether to play tennis, so the binary classification task is I play tennis, yes or no, and I do that based on 4 different features: how the outlook of the weather is that day, the temperature, humidity, and wind. And from this simple data set of observations over 2 weeks, we were able to build a decision tree. For example, we simply were picking a feature to start it with. Let's say initially random, like we choose the outlook feature. And if it's overcast, I always play tennis based on my data set. If it's sunny, then I'm still not sure yet, so I still have to ask an additional question. I have to ask whether it's going to be humid or not. And eventually, yes, if humidity, once I inquire the humidity, then I can find out, yes, if I can play tennis, like, yes, I play tennis or not. I don't play tennis. So, so we were sort of wondering if the order in which we choose these nodes is important. I think this is where we left last time. Do you have an intuition? Do you think the order is important? Yes, I hear yes. Yeah.
Yeah, you probably want the shortest trees.
The shorter, you want a shortest tree, yeah.
To get to the decision.
Yeah, exactly. So we'll see shortly that the order in which we do these things is important. So the order in which we pick some nodes will give us longer trees, shorter trees, and so on. Say that again?
Yeah, why do we want the shorter tree?
We want a shorter tree because it gives us fewer queries to make. If we have a shorter tree, then we can ask fewer questions, and we can get a faster prediction. So for example, here to get a prediction, for example, on this branch, we only have to make once, and if we're lucky to get to go down the overcast branch, but normally we require 2 questions to make. We'll see shortly what we mean. So the goal, so one potential goal is to have a tree that is as small as possible, and because of simplicity, because of a principle called Occam's razor, where we basically select a hypothesis that makes the fewest statements possible for it, and this is a principle that has been sort of, we've known this for many centuries. Essentially, like this was sort of like this Occam's razor principle was developed, I think in like Middle Ages by this person Occam. So we've had this intuition for a long time, but this is what we're applying here in machine learning, and we'll see that a lot. And the same principle is also used for regularization. We regularize other kinds of models. In general, however, finding the minimal decision tree that is consistent with the data is a very hard problem, and it's called an NP-hard problem, and it's a notion that I won't define. It's a complexity notion that I won't define here, but it's a very hard problem to find a minimal tree. However, we can find an approximate tree that is often like good enough. So and for that we can use a recursive algorithm that we'll see shortly. And the idea is that we'll find this tree that is very good, but we cannot guarantee that it's optimal. So let's see what happens. Let's see another example. So imagine you have a data set with four. So first of all, we have 2 features, A and B, and we have 4 cases. So if A is 0 and B is 0, we have 50 examples. If A and Z is 0 and B is 1, we have also 50. If A is 1 and B is 0, we have no examples with that. And if A is 1 and B is 1, we have 100 examples. And these are the labels. So the first 3 have a negative label. So let's say we don't play tennis. And for the final one, we have a positive one. So now the question is, what should be the first attribute we select? Should it be A or should it be B?
A.
Let's see. Yeah, so why A, actually?
So when A is 0, in both cases, there's two cases for A being 0 and two cases for A being 1, and for both cases of A being 0, we always label it as a negative.
Yeah.
So I think if we're just using this data, if we see that A is 0, we would just label it as negative.
Some other opinions, different opinions? Let's see. So if we choose A first, what is actually happening is that we have just a simple query and that's it. Like if A is 0, we choose negative, as our colleague said. If A is 1, it becomes positive, and we don't ask another question. We don't even inquire for B. Why is that? There's no example. We have no example for A is 1 and B is 0 in the data set, and we will never observe this case. This is something that so we actually know this because we have some idea of what a true function is, but in general we won't know. We will have no examples of this. So then in that case, all we observe is that when A is 1, then I play tennis. And we only have so that's why. And whereas if we split on B first, if B is 0, then yes, we don't play tennis. But if B is 1, we're still not sure. So we still have to inquire for A. So in this case, if we split on A first, we'll have a smaller tree for this particular data set. So what happens now if we get a few examples, though, for A? So what if instead of 0, now we have a few small number of examples? We even if we split on A first, we do have to inquire for B. Now it won't be sufficient because now in our data set we see some of these negative examples, and we have to account for them. So now which of these trees do you think is better? Yeah. The right one, yeah? Why? You take fewer queries at a time. Yeah. More of the time, yeah.
You just go to A0 100 times, or 100 examples, and then that ends the query.
That's ends the query. Yeah, yes. Exactly. So because if we assume that the test data set has the same distribution, like we'll have a lot of them like here and a lot of them here, then these queries will terminate faster. And we'll have only a few of these cases, of these scenarios that you have to ask for two different features. So that's the reason why, on average, we prefer the right tree, because on average we'll have to make fewer decisions. Yeah, is that clear? Yeah. Let me. Take that out. Yeah. So. Yes. So the main decision that the algorithm will have to make is to decide which queries you're going to to expand and to which of these attributes you're going to query and you're going to make. So in general, the idea is that we want to ask some questions such that the data set will be split quite well. So basically, the resulting nodes will become more pure. So for example, like the subtrees, so let's say if we end up with two subtrees, one subtree will have all the pluses and one subtree will have all the minuses. That's sort of what we want. We want all of these to, we want the splitting to separate the data set according to the label. So we want it to be relatively pure, these subtrees. So the most popular algorithm that has been developed, which does this, is called ID3. And it's based on information gain. So and this is actually a heuristic. So we never guarantee it, but it's a very good heuristic. So let's go shortly through it, if this would work. Because I clicked that. Yeah. So in order to develop ID3, we need to understand the concept of an entropy. So now entropy, when we talk about, for example, It's a concept that exists in information science, but also in physics, in thermodynamics. It exists in many disciplines, and basically it's a measure of purity, like how, or I should say impurity, how impure the data set is. In other terms, how uncertain a distribution is. If we have high uncertainty in a distribution, that's when we have high entropy. If we have certainty, we have very low entropy. So formally, this is defined as for a set of examples S. For example, let's say these examples are binary, so we just have pluses and minuses. We count the proportions of the pluses. So let's say we have 40% pluses, 60% minuses, and then we do this formula. So minus p plus log p plus minus p minus log p minus. That's the formula. And you can think of it more generally as the expected value of the logarithm of this random variable, if you think of it in statistics terms. So it's a weighted average. So it's weighted by these p pluses and p minuses, and the average is taken over this over the variable that we're talking about, like p plus and p minus, but transformed through a log. So it's a weighted average of the log of that variable. So if we generalize to k classes, this gives us the same formula, just now we do the sum over all the k's. How many of you have seen this before? So I have an idea of. Okay, a few hands. Yeah. So let's take a few examples. So let's get a bit of intuition. What is the entropy when all the examples belong to the positive class? 0. Yes. Why is that? There's no uncertainty. Yes. And if we look in the formula, so if all examples belong to the positive, then p plus will be 1 and p minus will be 0. So this is a proportion. How many? So these are all proportions. So this will be 1 log 1, which is 0. Log 1 is 0, minus 0 log 0, which is also 0. Log 0 does not exist, but if we take the limit and we do it like that, then it's defined in this case to 0. So it will be 0. And what about when all of them will be negative? Also 0, yeah. When exactly half are positive and half are negative? I hear some. It is 1. Yes. It's generally high. Yes. So in that case, it is 1 here.
So entropy being 1 means our maximum entropy, essentially.
Yes. So this is when we have, this is a case when we have high uncertainty. We don't know. It could be 50-50. It could be either, like when we have. So that's when the entropy would be 1 and it's high. So this is the plot, for example, of entropy as p plus goes from 0 to 1. And remember that p minus is 1 minus p plus. So for example, in case of a coin flip, the p plus is the probability of it landing on a head. So we have high entropy when we have high uncertainty, when the coin is completely fair and we cannot predict it. But if the coin is biased, then we start having much lower entropy. Or if the coin always lands on head, or always on tail, then it will be 0. This is another example of when, to get a bit of intuition. So these are 3 distributions. Do you think this is high entropy or low entropy?
Low entropy.
Low entropy. What about this one?
High entropy.
High entropy. Yes. So this is, we have very low uncertainty here. So we have low entropy. This is highly uncertain. Either of them could be equally likely. So that's high entropy. So now that we understood what entropy is, let's discuss. This is a very key concept. This is information gain. So So information gain is what we're going to measure in the decision tree. So when we take a node to split, we're going to compute this measure called the information gain, and we're going to do that for several variables. So remember, we had the outlook. This is an outlook, but we also have other ones. We have a temperature and humidity and so on. So we can compute this information gain for all these attributes. But let's see how we compute this information gain. So intuitively, don't look at the equation for now. Look at the tree. So imagine if we want to compute the information gain for the outlook node, we basically compute the entropy of our data set starting at this node. So that means if this is the root node, we compute the entropy over the entire data set. And then we subtract the entropy. So don't look at the equation, look here. So you subtract the entropy of each of these subtrees. We recursively computed the entropy at the top, then we compute the entropies on the bottom, and we do a weighted average of each of these entropies, and then we will subtract them from the top entropy. So this is what this equation is saying. So the information gain of the whole data set given a particular variable, so A here is outlook, will be the entropy at this node, at the top node, minus the weighted entropy of each of the subtrees. Yeah? Does that make sense? I see some yeses and nos.
But I don't understand why this is recursion instead of iteration.
Yeah, so this is over the entire tree. So we basically will be traversing the tree to compute this notion. So you see how you see you compute an entropy here, and then we compute the entropy of the subtrees. So we'll see shortly. So we don't. So the entropy, these entropies, you can compute based on the data set, like how many data points are still left at this node. But we'll see. Surely we will have to do that for all the nodes to build a tree. We'll have to traverse and compute these information gains. That's what I meant. Yeah. So and the idea is that we will this gain computes intuitively how much information we gain from splitting on this node. So intuitively, it means like how much information do we gain in the distribution by splitting on here. So for example, how much do we turn a distribution like this into something like this? That would be a gain of information, because now we know with much higher certainty that this will be a plus, and we can that's what the information gain will intuitively give us. So let's see in our previous example, was it better to split on A or on B? So let's see if we can compute the information gains. Intuitively, what do you think on this example? Do you think the information gain will be higher on B or on A? On A. Anyone who thinks it was higher on B? Yes, and the reason why it's higher on A is because you see, after we know the value of A, our data set is almost split. Almost. We have most of these values are on the right hand side, and we only have a tiny few left that are still unknown, so we have to inquire for B. But basically, most of our data set is already split, so we have very high information gain. That's the reason why if we split on A, it will be much higher information gain. But let's compute it in practice for, and I'll leave it as an exercise for you to compute the information gain on this example. But let's do the example with tennis. So let's compute the information gain on our data set. So again, we have the same setup. We have outlook, temperature, humidity, and wind. So the current entropy so we first compute the top level entropy. And this is, we count how many positives we have, how many pluses. So 9 out of 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, and negatives are 5 out of 14. So and then we compute the entropy of the entire data set. So it's minus 9 over 14 log 2 9 14 minus 5 divided by 14 log 2 5 divided by 14. So that gives us an entropy of 0.94. It's almost 1, so it's still high uncertainty. We don't know what is going on right now. Now let's see what happens if we start splitting on Outlook. If we take the node Outlook and actually split the tree in there, and or let's say we query this attribute. How many positives do I get if the Outlook is sunny? So if the Outlook is sunny, we have 1, 2, sunny, 3, 4, 5. Yeah. So there's and out of these 5, there's 2 negatives, 3 negatives, and 1 positive, 2 positives. So we have 3 negatives and 2 positives for sunny. Don't look at the numbers for now. So look here. So we have 3 negatives and 2 positives, and the entropy on this attribute is 0.97, using the same formula as here. Instead of these fractions, we put these ones. And we do the same thing for overcast. So for overcast, if the Outlook is overcast, so we have 1 positive, 2 positives, 3 and 4. So we have 4 positives out of 4 and 0 negatives. So here the entropy is 0, because we have complete certainty that these will be positive, that these are all positive. So that I will play tennis in this case. And we do the same for rainy, and we compute all these entropies for each of these subtrees, and then we compute the expected entropy. So we take each of these 3 entropies we computed, and we weight them by the number of elements in that subtree by splitting. Is that a question? Oh. Yeah, so, and once we do this weighted average of all these entropies, we get 0.69. So the information gain that we got was the original entropy, which was which was this one here, 0.94, minus this expected entropy, which is 0.69. So we get a value of 0.24. Any questions? Does that make sense? Now let's see if we do another different attribute. What if we do humidity? So humidity can be high or normal. We do the same thing for humidity. We count how many positives we have. So if humidity is high, we get 1 plus, 2 pluses, 1, 2. This is a minus, another plus, 3. So we get 3 out of 7 that are positives, and we repeat the same thing. So I think you get the idea, right? And we get that after we're doing all these calculations, we see that the information gain on this attribute is lower, is 0.16. So we do this for all the variables. We do for outlook, we do for humidity, we do for wind, and for temperature, and we get this information gains. And then we select whichever has the highest information gain, and that's the one we're going to split on. So in this case, because outlook has the highest information gain, we split on the outlook attribute. Yeah. So this is another example of so now we put these information gains that we just calculated. So we split on outlook. So then we put this as a root node in the tree. So far we have only this. We have just the root node, and we have 3 branches. And outlook can have 3 branches, so it can be sunny, overcast, and rain. And now we split our data set into each of these subcategories. So for sunny, we have day 1, day 2, day 8, 9, and 11. So we have 2 pluses and 3 minuses. And we do the same for overcast and rain. and we recursively do this. So then and this is what I was saying. So we basically now we recurse down on the tree. We do the same process for the sunny and for the rain. We then select another attribute to split on based on information gain.
Would we recalculate the information gain at these points again, or would we just use the values?
We would recompute it.
Like for sunny, we look at 1, 2, 8, 9, 11.
Yeah.
Only, right?
Yes, exactly. So for sunny now we only look at these this subset of the data, and you do the same thing. You split it into another attributes. Now yes. So you'll have a completely different numbers because you don't have the inside data set. And we repeat this process. We repeat this up until every attribute is included. For example, until we include all the 4 attributes, or until all the leaves in here have the same label. So, for example, in this case, for this category, all of them are pluses and have no minuses. So in that case, this is a leaf node. So we stop here. So we don't have to split any further on this branch. But on these ones, we have to split up until either we go through all these features, or until all of them are leaf nodes. So this is this is the example where if we split on sunny, we got it. So now this shows the subset of the data we're going to work with, for example, for sunny, and then we compute the information gain. We find that humidity gives the next the biggest information gain, so we split on humidity, and we do this on and on. So this is how you would implement it. So recursively. So this is a function definition. So if we have a function that induces a tree from our data set S, the first thing we do is that we ask, does S uniquely define a class or label? Like, for example, do all the data points in S have all pluses or all minuses? If yes, it means it's a leaf node, so then we stop there. And otherwise, we find the feature with the most information gain. So we go through all the features, sunny, outlook, humidity, and so on, all those 4 features. So, and we take the one with the maximum information gain, and then we split on that node and create a subtree. So this is where we create a subtree. So we add the children to our node S here. So for all the values k in values of f for all k's in these values, we take those values. So for outlook, it was sunny, it was overcast, or rain. So those are the values. We add the children, and then we recursively call the function in each of those subtrees. So this is how you'd implement it. So in summary, we learned how we can build a decision tree, and intuitively what it does is that it splits the hypothesis space or the parameter space. It splits it into all these different boundaries according to those queries that we make, and of course there's many trees, and we were trying to find often the best decision tree. And this particular algorithm, again, ID3 makes generally a greedy assumption. So at each step, you try to make a greedy choice. You choose the best node that maximizes the information gain. There's actually people used to think that these decision trees make decisions using all the data, but that's actually not the case. So actually, this might be a misconception. Do you think? Does anyone have any idea why this is not true? Why it does not make decisions based on all the data?
I mean, with each feature selection, we eliminate pieces of our data to look at, right? So I guess there could be the case where you get more examples later on that may not necessarily support the data that you assume to be true all the time.
Yeah. There's a bit more than that. Unless I misunderstood it. So apart from the new data points, what about the features?
We don't have to use all the features.
Yes, we have not used all the features so far. So for example, for this tree, sorry, am I going too much? Yeah, so here at the beginning, we have not used all the features. For example, we never used temperature at all. We only used outlook, humidity, and wind. We never used that column at all when we build this, for example. And so sometimes, so that means that not all data is used. This data, in a different tree, we could have used temperature, but not in this one. So it's not always the case that we use all the data. So another thing that can happen in decision trees is that we can overfit them. And we can learn too much of the noise or the variance. So imagine in this tree here, what happens if we have after we train it, what happens if we have this example in the test set where outlook is sunny, temperature is hot, humidity is normal, but wind is strong. So and this is a no. So if outlook is sunny, then we go on this branch. Humidity is normal, we go on this branch, and it's a yes. But actually, in our test set, it was a no. What do we do in that case? So one thing we can do is that we can always extend the tree. We can always do this. We can always add more nodes to the tree to account for this for new data points, for example. So now we can also query on the wind here, if it was weak or strong, and that would then account for this. So in general, with overfitting, so learning a decision tree might not always give you the best performance, and you have to use a validation set or a test set to test that. And there may be noise that the tree is fitting. There may be also like variance that the tree is fitting, and the algorithm might be making decisions based on very little data. So and a formal definition of overfitting is that a hypothesis S. So if a hypothesis S overfits the data, if there's another hypothesis H prime, such that H has smaller error than H prime on the training data, but H has larger error on the test data. So that's a formal definition of overfitting. So and again, we're talking about the reasons could be because there's too much variance in the training data, or the training data is not a representative sample of the instance space. There's maybe some bias even in the training data itself, or even that we split on features that are actually irrelevant and that don't matter at all. There could be also too much noise in the training data. And here there could be noise both in features or even in the class labels. So even the Y's, the pluses, could have noise. So in the as I told you, my research, for example, is on medical AI. And for example, in medical AI, you have data from patients and you have diagnoses. And sometimes diagnoses that are given by doctors sometimes are not correct. It can be, and in my case, when I was working with Alzheimer's data sets, we had around 80% accuracy of the labels given by doctors, because it's actually quite hard to make a diagnosis in some cases. So the doctors are not sure. So then in that case, you even have noise not just in the features, in the data of the patient, but also in the labels that you try to predict. So what are some solutions to avoid overfitting? So one idea is to prune the tree. By pruning the tree, we simply cut some leaves or some branches that are unnecessary. And the general idea is that this simplifies the decision problems. It simplifies the model, or it regularizes it. So we prune the children of a subtree if in general if all the children are leaves. And then we can reprune. We can cut all the we cut the last layers, and then we repeatedly do this until we're happy with the prune tree. So and then generally when we prune, we evaluate an accuracy on a special validation set, on a different data set than we train on. to test that they actually did something helpful. We will not do this on the training set. Anyone have any intuition? Why would it be bad to do it on a training set?
That'd be the set we were overfitted to, right?
Yes, exactly. That's the set we were fitted to, so we won't get any reasonable signal from that. Generally, if you prune the tree, we'll most likely on the training set we will likely lose performance, but we still overfit. So we have to do it on a validation set. And there's two basic approaches. One of them is post-pruning. So we do this. After we grow the full tree, after we run all the other, then we prune some of it. Or we can even do pre-pruning, which is during the building of the tree, we can at some point stop early. For example, stop the growing process of the tree early, when we determine that it's reasonable enough and we shouldn't go further. Yes.
What about like choosing one of like the lesser efficient options within our decision tree? Would that like not have an impact with the reasoning? Like we always choose the optimal one using the ST.
What about choosing a feature that is lesser optimal?
Yeah.
So you can do that, but I don't think it will solve. You can still have overfitting, even if you don't have actually even go with the greedy approach with the actual like best feature according to some criteria. That's because overfitting often comes from particularities of the training data. It's not due to the method per se of the algorithm. It's because the instance space, the training data, remember, it's always sampled from a much larger collection. Imagine you have a big box of objects and you only take a few objects. And then you kind of have to generalize. You have to make an assumption that all the objects in that box are the same, basically, or have the same properties. It might not be the case. Sometimes you might have outliers or other things like that. So, does it make sense?
Yeah.
So it won't, even if you do that, it won't solve it. So, yeah. Another very popular way to make sure we don't overfit trees is to build random forests. And random forest is basically, the idea is that we, instead of having just one tree for a problem, we actually build multiple trees. We build a forest of trees, and then the idea is that each of the tree will have some biases or some sort of like peculiarities, but over the whole collection of trees, they will kind of average out. And at the end, when we have a query, we pass it through all the trees, we get some predictions, and we do majority voting, for example, given all those predictions from all the trees.
And these trees are something that we could all run in parallel, right?
Yeah, you can run in parallel. Yeah. We can run it in parallel. We can, at the end, we can do voting. We can do averaging. If we have a regression problem, if we average all the labels or the scores. If we do regression, like if we want to predict the price of a house, then we can average all the predictions, for example, of the price, and so on. So any other questions so far about? Sorry?
Can you say how random forest random?
So you have, instead of one tree, you build an entire collection of trees. You build 10 trees or 100 trees.
How? If we are using a greedy algorithm,
Yeah. So you have to, you can't use just that. You can't use that. You can't use the ID3. You have to use some other strategies. You build, but the idea is you use different strategies. You build multiple trees. Random trees.
Yeah.
Yes.
Yeah.
Yes. And does it make sense?
So when we do the random forest, we cannot use the greedy algorithm to do the tree.
Because that algorithm would keep producing the same tree.
It will produce the same tree. Yeah.
Would there be any value towards, say, like, at the beginning of building the tree, choosing things randomly, and then using ID3 to build the rest of the tree? So that should still produce different trees, as long as some part of it has.
Say that again. You build random trees.
So when building our random trees for the forest, like you said, we can't just use ID3. But what if we were to start like the first two features or first 2 or 3 features, depending maybe a certain ratio of features, we choose randomly, and after you've randomly chosen these features, then you use ID3 for the
Got
rest.
it. So you could do that. You could do that. Yeah. Yeah, you could do that. Yeah. Another question. Yes. So the question. So it was. Yes. I will do that. I'm trying to not forget to do it. It was not a question, but more of a like sort of like an observation that it was. Our colleague was saying that if you could you, for example, build a few random trees initially in the first few nodes, and then afterwards run ID3 from the. So, for example, imagine you just have the first for the people on Zoom. So imagine you have just the first 2 or 3 nodes built randomly, and then run ID3 from level 2 or 3 downwards. And I was saying that yes, you could do that. I don't know the how successful this would be, but I think it would be worth sort of like trying it and seeing how it performs. Any other questions? Yes.
So if we use all the features in the tree, will it lead to more overfitting?
If you use all the features in the tree, will it lead to more overfitting? So far with the ID3 method, you're not guaranteed to use all the features in the tree. You can use only some of them. For example, in our case, we saw how we never use temperature. If you do use all the features, of course, not using ID3, then it depends. The short answer is depends on those features, what they are, and how relevant they are for the prediction problem. So, if some of them are irrelevant, yes, you can overfit. If you have some features that are relevant. But again, generally these we're not talking about random forests now, but these methods of building many random trees will sort of like cancel out the overfitting. Sometimes like these biases with each other, so then that will give you more robust classifier. So another thing we wanted to discuss. Let me see the time as well. 10:40. Okay, yeah, we have time. So let's finish. Let's finish a few more slides on continuous attributes, and then I think we'll take a break, or we'll do a quiz, one of them. So what do we do if we have continuous attributes instead of discrete? How do we build a tree when we have continuous attributes? We want to do let's say a regression problem. We want to predict the price of a house. We want to predict something else. The credit score. We want to predict temperature in 7 days or in 14 days. And temperature is a real valued number. So what do we do in that case? So one thing is we can discretize into ranges. We can do something like big, medium, and small. Alternatively, we can basically develop these nodes by splitting on thresholds. So for example, if you have a threshold that feature A is smaller than C, C will be a threshold, and this will partition the data into all of them that are smaller than C and all data points that are bigger than or equal to than C. And the information gain for these splits is computed in the same way as before. We see how many data points lie on both sides. We compute the information gain, and with those entropies, and then we choose which feature to split on. And how do we find a split with the highest gain? So let's take a short example. Let's say we have the length. We have some attribute which is the length of something that has several values. So it can be 10, 15, 21, 28, 32, 40, or 50. But this is a continuous number. It's just our numbers here are integers, but imagine this could be continuous. And the class here would be, this is negative, these two are positives, and so on, negative, two positives, and so on. So how do we find the split with the highest gain? So this is sort of the general approach. So for each of these features, so for example, for length, what we do is that we sort all these examples, all these numbers, according to their value. So these are already sorted. And for each ordered pair with different labels, so then we look basically at all the points that have different labels. So 10 and 15 have different labels. And then we decide we can split here, basically. We can do a split here, right in between 10 and 15. 21 and 28 are consecutive numbers with different labels. We can also split here. And same here, 28 and 32, we can do another split here. And 40 and 50, we can do another split here in between these. And the general idea or intuition is that something happened there. So something must have happened that somewhere in between 10 and 15 that this changed the class. This flipped the class from minus to plus. So something must have happened right in that interval. We don't know exactly where the threshold is, but something must have happened that's flipped the sign. So then we do the splits exactly when these flip the signs. And here the exact threshold can be either the midpoint. So for example, we can split right at the midpoint. So which is 12.5, or here would be 24.5, and so on, or 28 and 32. So this would be 30. Or we can also check gain at the rightmost threshold. So at 15, for example, or even the leftmost, either of them. The midpoint is generally used. Does that make sense? Okay. What do we do when we have missing values? So sometimes in many problems, in many data sets in ML, we have settings where we don't know the values of some features and variables. Again, actually, this was 5 years ago. We organized a competition of machine learning algorithms to predict Alzheimer's disease patients, and we have many data points. We had around 2,000 features for each of those patients, and some of them many features had a lot of missing values because those patients did not come to the hospital in certain days to do some measurements and so on. So I remember back then we had a lot of missing values in our data set. We simply did not have the information on those hospital visits. Some patients did not take certain scans, medical scans, or did some testing. So this is really it's a really common problem for many data sets. So what do we do? So some options is to throw away the instance if we can afford to. So in this case, if we have a missing value here, we simply throw away the entire row. If we can afford to, if we have a lot of data and we can afford to do that. Some other times we can fill in with the most common value of the feature, and we see that very shortly. Or we can fill in with all the possible values of that feature. Or we can even guess a feature based on correlations with other features. So if this data point is highly correlated or similar to some other ones, we can simply impute it like that. So for this example, this is a missing value example. So what do we do when we have outlook is missing in this particular prediction? So this is an example of filling in with all possible values. So what we do is that if the outlook is missing, we simply go down the tree and see, for example, temperature is hot, humidity is normal, wind is strong. So humidity is so a third of the time will be on this branch. So then we get humidity is normal. So that's a yes. A third of the time will be humidity normal, wind strong. So this would be a no. A third of the time would be a no, and a third of the time would be on the middle branch, which would be a yes. So then, on average, we can say that this would be 2/3 yeses and 1/3 no. So this would be a yes. Because of that, because of this sort of like majority voting. This is kind of similar to majority voting also. Sorry?
How does the 1/3 count?
Because it can be overcast and can lead to yes. So because we don't know the outlook, and if the outlook is overcast, it could lead to yes.
Okay. Is it gas? To free the outlook.
So-
easily?
So the 1/3 here is just assuming that each of these branches are equally likely. But the idea is that we then average, we go in the branches and we try to compute some prediction based on the remaining information. So if we assume this was sunny, we get a yes. If we assume that this was overcast, we get still a yes. And if we assume that this was rainy, we get a no. So we just average them out like that. Yeah. It's just a heuristic. It's not. It doesn't mean it's the best way to do it. But yeah. So if we have noisy labels, what do we do in that case? So what if for the same exact entry we have two different labels? And this was something that somebody asked last time, I remember. And again, we can throw away the entries with the conflicting information if we can, or we can also sometimes again do this kind of averaging, where we basically, if we have, for example, let's say 3 entries with yes, so let's say we had 5 instead of 2, so 3 yeses and 2 no's. Again, we can just say all of them were yeses, and then or just we discard the no's. We can do all kinds of things. So this is all sort of there's no best answer, and people do all different things. People discard the no's or so on, or do a majority voting.
I guess a lot of the decisions depend on the data.
Yes, the best decision, exactly. That's a very good remark. The best decisions depend on the data set, and you kind of understanding what is being modeled there, and what are the biases of each particular feature.
Going back, if it's the same missing information and everything else is the same, how could they have different labels if we're using the system you described before, where we have 2/3 yes, 1/3 no?
I'm sorry, but I didn't understand.
If we're missing the same exact information in 2 data points, and the rest
This is not about this. This is about this. Yeah. Yeah.
Observed data points that have conflicting information.
Oh, okay, never mind.
Yeah. Oh. Sorry, I didn't. Yeah. Well, okay. So these are the same data points. There's no missing information here. They just have conflicting labels in this example. Yeah.
I thought it was connected.
Yeah. Yeah, I mean, we're sort of going through some issues, here, what do you have missing data? What if, you have conflicting labels and so on? Sort of how do we deal with these things? And in general, sort of there's no, for many of these things, there's no single best answer. People again do different things depending on different data sets, and this particular remark here, I want to stress out, ML is really an experimental field. We still don't know what are the best approaches to many of these things. So people try. We're still trying. People are trying all these different strategies and so on. And sometimes some work better than others, depending on the problem you're doing. So, and what if the labels are numeric? We're talking about continuous. We can build the trees where the labels are numeric. So basically, you have a continuous value here, like 0.3, 1.8, and so on. So it's very similar. Now instead of having binary labels or categorical labels, you have numerical values. And I leave this for you to read at home. But there's sort of there's been a lot of research on the history of decision trees. But I'll let you read this at home. And now let me see the time. 10:52. Shall we do a quiz and take a break, or swap it around? Shall we first take a break and then do a quiz? Let's do a quiz first? Okay, let's do a quiz first.
I feel like I get to decide sitting up here in front.
Yeah. Is that okay with everyone? Okay. So So you go on this link here, joinmyquiz.com, and this is the code. Everyone signed up? Yeah? Anyone has not signed up? Anyone who hasn't? I still see a few people coming, probably. People on Zoom can see my code, right? Yeah, the game code. I'm giving 10 more seconds. I still see some people joining. Okay, let's start. 3, 2, 1. When does information entropy have a high value, and why? Why does the formula use log 2? What could be the reason why logarithm is used? And why in base 2? 12 seconds left. 8, 7, 6, 5, 4, 3, 2, 1. Let's see. It has a high value when positives and negatives are roughly equal. Yes. Yes, that means this high uncertainty. It can be either positives or negatives. High value of 0.5 are as equally likely for both outcomes, hence more uncertainty. Let me see from here. So yes, at the proportion of being 0.5 when p plus or p minus are 0.5. Yeah.
If our max entropy is when p is equal 1/2, then log base 2 just makes it really convenient for math, right? So we get a 1 value.
Yeah. Yes, exactly. So high entropy is when they are equal. Um, when the data is more evenly balanced between classes. Yes. It is binary classification problem, so there are two classes. So I'm seeing some attempt at number 2, but let's read some more. So when the data set is evenly split between two options. So I think we get some clarity. So essentially when this is split, for at least for the first one, that's when the entropy is high, when there's equal proportion. But what about the second one? Let's read a bit more. So it uses log 2 because the highest entropy should be when p equals a half. No. When there is equal probability, when the highest uncertainty between plus and minus. Let's read some more. I have to stay here. Yeah. No. Well. So yes, but I want to see the answer for the second question. The max value of the graph, since this is where nobody answered the second question. Aha. Equal distribution between positives and negatives, which is a high entropy. Entropy is measured in bits. Yes. This is on the right track. Yes. What does that mean? We when you do log 2 of something, you're basically computing how many bits you need to represent that concept. So for example, take our alphabet. English alphabet has 26, 28, I don't know exactly, 26 letters. So you need log 2 of 26 to represent that number in bits. So you need around 4 or 5 bits. How many? Like 2 to the power of 4, 16 to the power of 5, so 5. So you need 5 bits to represent all the letters in the English alphabet. Yeah. So it's a measure of how many bits you need to represent all those variables. So the entropy is then so this log of something is basically telling us how many bits you need to represent that concept. And when you weight it by these weights, you do a weighted sum of logs. You basically measure on average how many bits you will need for the entire thing. Yeah? Okay, next question. And we won't go to the fourth one, but we'll stop there. Okay, 3, 2, 1, go. Regarding information gain, mark all true statements below. Fifteen seconds left. So let's see what happens. So okay. So let's go through them one by one. Am I seeing everything here? Weights are yeah. So the first one. So these weights, the modulus of SV given modulus of S, are the percentage of data points in a subtree. Is that true? Yes. So basically, this counts. So the cardinal of S is the number of data points in S. The cardinal of SV is the number of data points in the subtree. So we have to weight the key thing in the formula, which you can see. I don't know if I can zoom it. What does that do? Yeah. So in that formula, we have to weight these entropy terms in the subtrees by the proportion of data points that they belong, because sometimes we don't care too much about that much about a branch which has a tiny number of data points. So we'll weight it much less than the ones which have a much larger number of data points. So yeah, so this is correct. So these weights represent the percentage of data points in a subtree. Can the information gain be negative? No. Any idea why?
That imply we're unlearning things.
Yeah.
And observing more information is never going to be bad. Maybe useless, but not bad.
Yeah. So we have not done this, and we won't cover it in the class. But the information gain. So there's two things. So the information gain between S and A, so it can be written as the entropy of S minus entropy of S given A. If I had a sponge as well. And you can kind of, if you expand this and write this out, and I won't do it here, you can find out why it will always be positive or greater than, or at least 0. But there's another way you can write it, which is you can write as something called the KL divergence, the Kullback-Leibler divergence between two functions, between some function f and another function g. I won't go into too much detail, but essentially this KL divergence, it's a distance measure between different distributions, and it can never be negative. So the information gain. So you can also write it also as a KL between two functions, and this will always be positive, or at least 0. It can also be 0, and yeah. The third one. So gain of S and A can be interpreted as the information gained from knowing the value of A in set S. Yes, this is how much information we gain from knowing that particular value of that attribute. What happens when a feature A is relevant? Is that will the information gain be 0 or very low? Is that true? Yeah. That is true. Okay, one final question, and then we'll take a break. Yeah? Actually, any questions on this before we move? No, okay. Let's go. 3, 2, 1. How many queries do you estimate roughly that a tree has? And how can you tell from the figure? this is a longer question. Can you see the rest of the question in there? Because it has a second point. Okay. Okay, let's start looking through the answers. You can still write a few more things. So 3 queries is it has 3 distinct clusters. What does everyone think? No? That's the number of labels. It's not the number of queries. So it's the number of Ys. So it looks like there's 3 classes, 1 to 5, 8 queries, green. I see, yes, so I see quite a few answers. So 200 red, no. There is overlap of points in different boundary regions. 2 queries, red. What were the other 2 questions? Because I couldn't see them.
Which boundary is the root node, and what do you think this will overfit?
Yeah. So, which boundaries are the second question was which boundaries are the root node, and do you think this will overfit? So first, let's look a bit at the picture. So, wait. So 3 is the number. Are we clear that 3 is the number of cluster of labels we have? Red, green, and blue here. It's not the number of. So queries are different. Queries are the number of nodes in the tree. Like for example, in the case of the tennis example, we had only 2 labels. I play tennis and I don't play tennis. But we had 4 attributes. There was the outlook, the temperature, humidity, and there was another one, and weather, like rain. So, so here we have 2 features.
Could it be 1 query maybe?
Sorry?
Is it 1? Because we got the little islands kind of sitting out in the middle of the boundary.
Yeah. So each of these thresholds, like a threshold like this one here, each line is a query. This is because in the tree we compare the value of one feature, like this one, if it's bigger than 5, for example. So that creates a threshold, like this vertical line here between red and blue. So let me see. So this will be a threshold, this vertical line. This other line here will be a threshold. This will be a threshold or a query. So all of these, and we have a lot of them. We have here, 1, 2, 3, 4, 5. So in total, it's around, I think, 87. Yeah. So, but I wanted, the reason why you didn't have to count, the reason why I asked this question was so I wanted to see if you understand a bit of difference between kind of like what's a query, what's a label, what's a feature, which are all different. We have 2 features, 3 labels, red, green, and blue, 2 features, and many queries or nodes. So this whole tree will have 87 nodes in the tree. 87, because all of these thresholds represent a different query.
Then I guess the root query would probably be on 0, since that's our biggest boundary.
Yeah. Oh, go on, develop that idea a bit more.
Looking at all our boundaries, our biggest one is right on this x.
Somewhere here, where do you think?
The vertical one.
Vertical.
Down there, yeah, because it's really big and
Yeah.
it seems to make a lot of decisions right at the beginning.
Yeah.
where everything
Yeah.
else is much
Yeah.
smaller and dividing much smaller groups of.
So the root node would be a node that maximizes the information gain. Remember, so it would be something that would be somehow in the center here, that somehow splits at least 2 classes quite well, or separates at least a big chunk of the data on one side versus another. So maybe this one would be a good one because it separates all the green ones mostly to the left side, for example. And that will give quite a large, big information gain because of the separation of these ones. Or maybe this one here, one of these with the reds, for example, could also be like a root node. We don't know in this case. I don't know. I have to, but this would be one of these would be the first node in the tree. And the third question: do you think it overfit? Well, I want to hear some opinions. Let's hear no. Who thinks it did not overfit? Yeah. So I heard something along the lines of that it didn't overfit too much because most points are correctly classified, and that's true. Yes, at some extent. So I still think it did overfit, and this is more of a qualitative sort of judgment. And in some parts, like for example these green lines here, for example, like this is where like these regions where definitely like this green line overfit.
Like islands of labels.
Yeah, islands of labels.
Random straight green lines, a couple of random puddles of red. And
this green, yeah, exactly. So this green part, yeah, exactly. So some islands of red here. This shouldn't be here. You can see how the data still has some noise, but yes. Is it clear with this question? Yeah, it was tricky. I know. Okay, so let's take a short break, a 5-minute break, and then we'll do another. Oh. Okay, so in that case we'll finish. I didn't realize we're so late. So we can do the last question. The only problem is it's on k-means, which I haven't taught yet. which I was planning to. So I think we're just going to finish early today, unless you have some questions, some final questions on this. No? Okay. Could everyone hear me well on Zoom? It's okay.
Thank you.
Yeah, you're welcome. I'm trying to see if this was good. welcome. Welcome. Yeah. So we're finishing early today for those on Zoom as well. See you next week.
Why can't we use Gini index for side topic?
Yeah, no, it's I'm ending there.
We use entropy to make the split, so can we not use Gini index instead?
The Gini index.
Yeah.
Yes, that's something you could use as well. Like so, you can use you can use a lot of other types of.
No, I mean, I thought is entropy better? Like,
So yeah, I think there's some arguments about the fact that entropy is better, and according to some criteria.
because I think Gini index has a shorter range of 0 to 0.5.
No, but you're right. You're right. You can use a different measure to select those nodes.
I mean,
Yeah,
I
yeah.
thought, like, is it not as good as entropy or something?
Probably there's some consideration, some theoretical consideration. I have not read the paper like from 30 years ago on the ID3 algorithm exactly.
Yeah.
What is the property that entropy gives you? Which I still it maximizes this KL divergence. Yeah, but again, it's a choice that is made. Like you might not want to maximize that. It's the same how in these models, like you define a loss function and you want to minimize that loss function. So how you choose it is there's various ways you can do an L2
Because
loss. Yeah.
Entropy measures randomness, like how uniform the thing is, but Gini also measures like how less diverse it is. Like,
Yeah,
I mean,
yeah.
how you, it's also measured.
Yeah, it's very similar. It's
So
very
it's like,
similar.
is it
Yeah.
same or?
The
There was
way-
this question about coefficient, so I misinterpreted information gain for Gini, but no, it was still correct. I mean, Gini also cannot go negative.
Yeah.
so that's right.
No, but it's close. It's close. Yeah.
Not entropy. Like, is Gini same as information gain?
No, I think Gini. I think it's more used in economics. That's why I'm also less familiar with it. It's like it's a measure that I think I thought was more developed in economics to measure, like in social sciences, to measure inequality between like distributions of like things like income, like and so on, or like in
Income per
populations. Yeah.
capita,
Yes. So and what considerations they had in mind when they developed the Gini index, I do not know. I do not know where it came from. They usually when they derive some of these, they start by saying something like, "Oh, we want to
Like that particular
max."
field wants to use it,
Yeah. But they kind of say, "Oh, we want to measure inequality." More precisely, we want to find an index that maximizes something. That maximizes, I don't know, or that is low when there's perfect equality, I think, and it's like high when there's inequality and stuff. So yeah.
Yeah, it was
Yeah,
also
yeah.
similar, like, but instead of like information gain should be
It's similar.
high,
It's very similar. I know.
Gini should be low.
I know,
when
I
the
know,
spread
I
is
know,
made,
I know.
yeah, so it's kind of like inversely proportional, right?
I'm actually curious. Well, no, entropy versus Gini.
Yeah, Gini impurity.
Yeah. When should I use Gini impurity as opposed to information gain? Yeah. Gini impurity and information gain are pretty much the same, and
Right,
people do
there
use
was-
the values
yeah, it's solid
interchangeably.
concept too.
Yeah. So you don't compute the log.
I think it is computationally easier. No, when we were implementing the algorithm, we used Gini.
Yeah, I know. So I'll tell you, like in practice, often they don't. They make some. They give you some differences, but sometimes they're not actually crucial. For many applications, they might not. Even if you do it with Gini, it
I
will
was just
generally
wondering,
still.
like, if one is
Yeah.
better than the other that way.
Yeah. You see, the thing is, yeah, you do p log p instead of p squared. And log is still like a monotonic function, so
It is also increasing.
yeah, increasing using some. Yes, I mean, so these functions might have very similar maxima, but even though the curves might be different.
So it depends on situation then.
Yeah, you see how the functions have the same maximum.
Almost similar.
Almost the same. Yeah. Yeah, it's not too different. Yeah, you can use either. Yeah. Yeah. Welcome.
Thank you.
Welcome.